gentlemen, our focus today is going to be on covalent bonding and oxidation numbers. So last time you were with us, we talked a lot about type 1 and type 2 nomenclature, that is nomenclature between metals and nonmetals. Well, today our focus is really going to be on the concepts of covalent bonding, which primarily occurs between just non-metal elements. We're also going to dive in and talk a little bit about the importance of oxidation numbers and being able to determine them in covalently bonded chemical compounds. This will pop back up when we start talking about redox reactions in our chemical reactions unit. So our learning targets for today, hopefully by the end of this video you will be able to identify which type of compounds are covalently bonded, that is, what are type 3 elements. Use type 3 naming rules to identify the names of compounds and their formulas, and you should also be able to assign oxidation numbers to a variety of chemical compounds. So today we have just a couple of key vocabulary terms here. We're going to look at type 3 compounds. We typically call these molecules versus compounds themselves. We'll also use the term prefix, which I'm sure you guys are really going to struggle with the term prefix. I mean, that's a hard one there. And then we'll also take a look at oxidation numbers. So when we look at type 3 compounds, they're better known as molecules as they are covalently bonded, and they typically will start with a non-metal. So for example, carbon dioxide, dinitrogen monoxide, etc. So again, what we'll look at is we're going to look at compounds that only have non-metal components. So previously we looked at metal binding with non-metal. Today we're going to look at non-metals binding with non-metals. So just as a reminder of what your nonmetals are, it's pretty much everything to the right of this stair step. So if anything starts pretty much with any of these elements over here, either on the stair step or to the right of the stair step, typically they will be a type 3 chemical compound. And so you'll need to make sure you use the appropriate naming rules. So type 3 naming rules are much more straightforward than type 1 or type 2. Simply, we just use prefixes that represent the number of atoms in the compound. So that's when you've got mono, di, tri, tetra, penta, hexa, hepta, basically all the things that you've probably learned from your geometry class. There's no need for any charges or any Roman numerals. So for example, CCl4, C is carbon, Cl is chloride, and then we add tetra in front of it because that's the number, or that's the prefix that represents the number 4. So keep in mind that when we actually do look at these, you notice that there's a prefix called mono, which means 1. We do not use that in the first element that we're using. So you notice it's not monocarbon tetrachloride, it's just carbon tetrachloride. The only time we would use mono is if we have the second element being just 1. So just kind of keep that in the back of your mind with some of these naming rules. Alright, so to just get started on some nomenclature practice problems here, let's take a look at some of these examples. So the first one we have is PCl5. Well, hopefully you know that P is phosphorus. P is phosphorus, and we don't have any root there. Now the second one is Cl, so it's going to be chloride, but because there are 5 of them, it is going to be pentachloride. So the first one is going to be phosphorus pentachloride. The next one, H2O, which hopefully we know is water, but in order to give it its proper term, H2, so H is hydrogen, but there's a 2, so we're going to call this dihydrogen. And then O by itself, again, it's the second one, so this would be monoxide. So H2O's full name is dihydrogen monoxide. The last one, C4N7, probably not a real compound, but let's take a look at it anyways. So C is carbon, 4, so that's going to be tetracarbon. And 7N is going to be hepta. nitride. Again, we still add our root at the very end, so it's not going to be tetracarbon heptanitrogen, it'll be heptanitride. Taking a look at the few more of these down below, writing it the opposite way, we have dinitrogen pentoxide, it's dinitrogen, N and di, 2, pentaoxide, O, 5. Okay, simple enough. Carbon hexafluoride, C for carbon, hexafluoride, F and 6. Tricarbon hexahydride, tricarbon, so it's going to be C, 3. Hexahydride, hydride refers to hydrogen, this is going to be H and 6. Okay, pretty straightforward on how to write those chemical compounds. So hopefully now that you have a really good idea about nomenclature, let's continue and talk a little bit about oxidation numbers. Now, oxidation numbers are the same thing that we've been referring to when I've been using the term charge, when we've been looking at type 1 and type 2 nomenclature. The oxidation number itself just simply refers to the general distribution of electrons around an atom, and again, they're very similar to formal charges. So we take a look at these primarily with covalently bonded compounds, although we also use them quite a bit for ionic. You do need to keep in mind that very much like when we're looking at charges, when we're determining the name of a compound, that the sum of all of the oxidation numbers is equal to 0. And if it happens to be a polyatomic ion with a charge on it, then the sum has to equal that particular charge. So one of the examples that I'm going to give you here, assign the oxidation numbers to CF4. Well, given the rules that are up here on the right, F is always a -1, and there are 4 fluorine atoms. Therefore, the net negative charge is -4. Since the compound itself is neutral, the oxidation numbers must equal 0. So if fluorines are -4, then carbon must be a +4, as the molecule is neutral. So again, if you use the ones that you know, primarily primarily oxygen, fluorine, hydrogen, you'll typically come to the right conclusion, assuming that you do your math correctly. Let's take a look at a couple of examples of assigning oxidation numbers. So let's assign the oxidation numbers to the following. We have some nitric acid, we have a phosphate ion, and then we also have sodium sulfate. So let's start with the first one, HNO3. Well, according to our rules here on the right, hydrogen, HNO3. Hydrogen is always a +1. We have one of those. Oxygen is a -2. So with each oxygen, we have a -2. There are 3 oxygens here, so that is a -6. Remember that these have to balance out to equal 0. So the the oxidation number on the nitrogen, in order to balance out to be 0, is going to be a +5. So you see, just follow the rules over there on the right-hand side. You have no problem figuring out and assigning oxidation numbers. Let's look at another problem. PO4 with a -3 charge. So if we take a look at our rules again on the right, oxygen is always a -2. We have 4 oxygens. So 4 times -2, that gives us a total of -8 for our oxygens. Now here we have a charge that's assigned to it, so the sum of all of our oxidation numbers is not going to equal 0. It's going to equal -3. So what plus -8 equals -3? Well, hopefully you said a +5. Okay, and that's going to be our oxidation number for phosphorus. So again, follow the rules, have no problems whatsoever. Let's do one more practice problem. Na2SO4. Well, again, let's follow the rules here. Group 1 are +1, so each of these is +1. So we have a total of +2 here. So each sodium is a +1. Oxygen is always a -2. There are 4 oxygens again, so 4 times -2 is -8. Remember that all these must balance out to equal 0, so the oxidation number on sulfur is going to be a +6. 6 plus 2 minus 8 equals 0. So again, just follow the rules on the right hand side, assign oxidation numbers, and you'll have no problems whatsoever. So long story short, we've gone through a lot of different material today. We've talked about type 3 chemical compounds and understanding how they're covalently bonded, along with determining and utilizing the nomenclature that's associated with it. We also took a brief look at oxidation numbers that we can assign to particular elements in a compound. It's a pretty straightforward process, pretty important process, especially when we start talking about a variety of different chemical reactions. Hopefully you got what you needed from this video. Hopefully we met all of our learning targets, and if you have any questions, feel free to contact me. Have a great day, guys. We'll talk to you later. Bye-bye.